So last time we introduced the generalized momentum. Pi, and that was given by the partial derivative of the Lagrangian with respect to Qi dot. And so we say that Pi is the generalized momentum that is conjugate to the coordinate Qi. So each coordinate has a generalized momentum. And we saw in a few examples that that generalized momentum can be linear momentum, or it could also be angular momentum. And presumably it could be more complicated things. So if we look at the Euler-Lagrange equation, we have d by dt of diL by diqi dot minus diL by diqi equals 0. So the diL by diqi dot is Pi, right? So this is d by dt of Pi equals diL by diqi, or Pi dot equals diL by diqi. That's simply rewriting the Euler-Lagrange equation using p's instead of Qi dots. So you see here that if diL by diqi equals 0, so the Lagrangian does not explicitly depend on the Qi. It could depend implicitly on the Qi, but not explicitly. In that case, we see that Pi dot equals 0. Or we see that Pi equals constant. So we call this coordinate, if diL by diqi is 0, then we say that Qi is a cyclic coordinate. And so for each coordinate that is cyclic, the momentum is conserved. So after that, we looked at the Roothian, and we found that we can introduce this quantity R, which we call the Roothian, given by L minus the sum over I of beta I Qi dot, where the beta I equals the generalized momentum of the cyclic coordinates. So if we introduce the Roothian, we found that the equations of motion are greatly simplified. So the Roothian allows us to effectively eliminate all the cyclic coordinates from the problem so that we get two sets of equations of motion. So let's say if Qi for I equals 1 to k, so the first k coordinates are cyclic, the equations of motion are given by, for the cyclic coordinates, Qi dot equals minus di R by di beta I. So that's for I equals 1 to k. And then for the other coordinates, the equations of motion are unchanged. And so we just have the Euler-Lagrange equation. d by dt di R by di Qi dot minus di R by di Qi. equals 0. In what section of the notes is the Ruthian addressed? So that's in, it's the end of chapter 4. Is it not on the online version? I thought it was, though. Yeah, so it's the last part of chapter 4. So the Ruthian is like, it's interesting, but it's not necessarily super useful. But what we're doing in this course, in undergrad, you should have, in principle, have seen the Lagrangian and things like that. So I'm not so interested in this course in spending a lot of time doing examples of solving the equations of motion. But I'm more interested in looking at the mathematics and some of the stuff in classical mechanics so that you get later on a better understanding of quantum mechanics. So the Ruthian here is sort of a mathematical procedure that is pretty, and it should be interesting, and as you'll see, it fits into this larger theme of trying to have a very analytic approach to classical mechanics. Okay, so don't worry if there aren't 8 million examples either in the class or online of applying the Ruthian. It's more I'm interested in you guys going through the process of working with these equations and seeing how you can manipulate them rather than applying it to a set of examples. Okay. And so, continuing on that, we're going to move into, well, is there any questions actually about this, the material from last time, or the Ruthian? So it's fairly straightforward, right? And I showed you a procedure last time when we did an example, and we've done several examples in the notes when we were looking at the Lagrangian, where there were cyclic coordinates. So you're welcome to go and try and resolve those problems by using the Ruthian and see if you get the same answer. Okay. So now that we've covered the Lagrangian and some examples of physical situations, we're going to move into sort of more abstract area of classical mechanics. And so it has a sort of beauty to it. And helps you understand, have a deeper understanding of quantum mechanics. So this is chapter 5. And we're going to look at conservation laws and symmetries. Okay. So let's start with a simple example, which is 5.1 in the notes. So let's consider a particle in a central force potential. So an example of a central force is gravity, right? The force depends on the distance between two objects. Or the Coulomb force is also a central force. And in principle, you can have central forces that don't depend as 1 over r squared, but could go as 1 over r, or 1 over r cubed, or fourth, or whatever. Okay? And we're not going to care what the shape of it is. So let's write out the Lagrangian and Cartesian coordinates. So Lagrangian and Cartesian coordinates is going to be a half m x dot squared plus y dot squared plus z dot squared minus this potential. And the potential, so let's say, it's a gravitational potential, and we care about, the big mass, and the big mass is at the origin. So the potential will depend on your distance from the origin. So the potential we can write as function v that depends very generally on the distance to the origin. So square root of x squared plus y squared plus z squared. Okay. So if we look at this Lagrangian, we should now start having the reflex to look for cyclic coordinates. So we have 3 coordinates, x, y, z, and all 3 of them appear in the potential. All right, so there are actually no cyclic coordinates. So we conclude that there are no cyclic coordinates. And thus, no conserved generalized momentum. Okay, fair enough. Let's model the same situation in spherical coordinates. In spherical coordinates, we have L equals a half m. And now you learned this in assignment 2. The kinetic energy in spherical coordinates is r dot squared plus r squared theta dot squared, where theta is the polar angle, plus r squared sine squared theta phi dot squared, where phi is the azimuthal angle. And then minus, now the potential in spherical coordinates only depends on r. And so let's look for cyclic coordinates. So r is not cyclic because it appears both in the kinetic energy and in the potential energy. Theta is also not cyclic because it appears in the kinetic energy, the sine squared theta phi dot squared. However, phi is cyclic. Oops. So phi is cyclic, then of course the generalized momentum that goes with phi is a constant, or is conserved. So p phi, which is given by di L by di phi dot, in this case it's equal to mr squared, mr squared sine squared theta phi dot. And that's got to be equal to constant. So what's this p phi is the angular momentum about z. All right. So this is interesting when you think about it. The choice of coordinates leads to finding conserved quantities or not. So if you use Cartesian coordinates in a central potential, of course, none of the linear momenta are conserved. And so you conclude that there are no conserved quantities. And so conserved quantities are good because they make the problem much easier to solve, right? Because here phi is given trivially. So it appears that the choice of coordinates can uncover quantities that are conserved. And so there's clearly optimal choices of coordinates. So let's write that down. the choice of coordinates seems to uncover conserved quantities. So the question is there a method to determine the optimal choice of coordinates? And the answer is yes. And that is done by using what we call canonical transformations. And we'll see those 2 chapters from now. And so this canonical transformation, to give you a flavor of what's coming up, is a method in which that tells you how to choose coordinates so that all of them are cyclic. So there exists a coordinate transformation to a new set of n generalized coordinates where all of those coordinates are cyclic. And so then the equations of motion are trivial because they're all just one-dimensional, first-order differential equations because they're all momentum is constant. So the equations of motion become trivial. However, the part that's not trivial is how to find the canonical transformation. And so we'll see that later. Yeah, Jason, you have a question? Does this work for any system? Well, yes. In principle, it works for any system. I think you have to have the caveat that the system must be conservative. So, friction forces and things like that. I'm not sure you can always do a canonical transformation. But then when you do, proper physics, sort of a generalized theory of physics, all the forces are conservative, right? Because all these friction forces and typically non-conservative forces are usually internal forces. So if you do a proper modeling of the system, you should have only nice forces. And in that case, yes, I think you can always do a canonical transformation. It might be mathematically impossible, but physically it's in principle possible. All right, so you might have like a transcendental equation or something like that. So we're going to leave that thing about canonical transformations to a later chapter. And in this chapter, we're going to learn a little bit about what symmetries can lead to conserved quantities. And so this is a theme that you've probably heard before, and we've already seen it a few times in this course, where if a system is invariant to some symmetry or some transformation, then a quantity is conserved. And so that's what we'll work on in this chapter. We already saw in the case that when the Lagrangian does not depend explicitly on time, we found that energy is often conserved. All right, so for example, if gravitational energy changes with time, then energy wouldn't be conserved in gravitational motion. But if gravity is fixed in time, then energy is conserved, and gravity would be a conservative force. Okay? So this chapter is going to be rather formal mathematically, but it has some sort of neat consequences. So we're not going to be able to get too far because I have to leave early today. But let's get started with continuous transformations. So write a continuous transformation, so the overlying theme here is there must be, a particular choice of coordinate system might uncover more conserved quantities than a different choice of coordinate system. So one can change from one coordinate system to another. So we're going to study what we call continuous transformations. So continuous transformation from one coordinate system to another can be written as Qi prime, so the transformed quantity depends on the untransformed quantities. So Q1 to Qn, Q1 dot to Qn dot, time, and then some parameter that can be varied continuously. So, for example, think of a translation of the coordinates. You can translate the new coordinate system by a certain distance. We call that distance epsilon. And so you can change epsilon in a continuous way, and that changes continuously how the transformation behaves. Okay, and we'll see a couple examples. In principle, time can also be transformed. So we should write that t primed is equal to, again, also a function of everything else. So the Q1s to the Qn's, the Q1 dots to the Qn dots, original time and epsilon. So since epsilon can be varied continuously, in principle you could also make a bunch of tiny transformations and sum them all up to be equivalent to the total transformation. So think of translating the axes. The sum of a bunch of tiny small translations is equal to one big translation. So the idea of a continuous transformation is that it can be broken up into infinitesimal transformations. Sorry, just give me a second here. I have to answer a phone call. Okay, sorry for that. So now I lost my train of thought. Yeah, so a continuous transformation can be broken up into a bunch of what we call infinitesimal transformations. So I'll give the example of translation. You could think of a rotation of the coordinate system as well. A rotation of an angle theta is the same as the sum of a bunch of little rotations, delta epsilons, that sum up to theta. Okay? So that's what a continuous transformation means. So an example of a not continuous transformation is, for example, a mirror symmetry. Right? There's no tunable parameter that you can make it transform or not, more or not, right? So reflection through a mirror it's a set transformation, so it's not a continuous transformation. Okay? So example, translation and rotations are typically the only ones you really need to consider as continuous transformations. So a continuous transformation, like I said, continuous transformation can be broken up into a series of infinitesimal transformations. In examples, I'll say not reflection by a mirror. Okay, so in that case, we only need to consider infinitesimal transformations. So that was the whole point. So consider an infinitesimal transformation. Oops. Qi primed would be given by Qi plus delta Qi. And we can write that as Qi so the delta Qi, I'm going to write it as a function Fi of the coordinates. So Q1 to Qn, Q1 dot to Qn dot, and T without epsilon, and I'm going to multiply that by delta epsilon. Okay? So I can parameterize any infinitesimal transformation this way, right? So it depends on epsilon, or in this case delta epsilon, and it changes Qi by an infinitesimal amount. So then Ti primed, whoops, not Ti, just T primed, only one time. T primed we would express as T plus delta T, and I'm going to write that as T plus G, a different function of G, of the Q's, Q1 to Qn, Q1 dot to Qn dot, T, delta epsilon. So for each Qi, there's going to be one Fi, and then for T, there's only one T, so I'll have an index, and then that function will be called G. Okay? And so what we're really saying here is that delta Qi, just rearranging the top equations, which is Qi primed minus Qi, that's equal to Fi delta epsilon. And similarly, delta T, which is equal to T prime minus T, that's going to be equal to G of the variables. Times delta epsilon. Okay, so the F and the G's are what determine the transformation. So let's do a couple examples of determining F and G. Okay. Let's do example 5.2. So let's do the example of finding F and G for a translation along the x-axis. So a translation along the x-axis, if I write this as a continuous transformation, x prime is equal to x plus epsilon, y prime is equal to y, z prime is equal to z, and t prime is equal to t. Right? So that's a simple translation along the x-axis. Not an infinitesimal, just a normal one, by distance, epsilon. So the infinitesimal version, and on the next page, infinitesimal transformation, x prime is equal to x plus delta epsilon, y prime is equal to y, z prime is equal to z, and t prime is equal to t. So let me compare this with the form that I had, which is that Qi primed is equal to Qi plus Fi delta epsilon. So in that case, we find that F1, which we'll call Fx, is equal to 1, just by comparing the two equations, right? Fi for the x equation is just equal to 1. And then all the other ones are equal to 0, because the other coordinates don't change. And then G, which is the one that would go with the time, is also equal to 0. Okay? So for a translation, the idea is you want to characterize the infinitesimal version of the transformation, and so you need to find the f's and the g's. So for a translation, they're all equal to 0 except the f that corresponds to the coordinate being translated. If it's a translation in that in a particular direction. And the other example that we'll look at is example 5.3. We'll find f and g's for a rotation. So if we have a rotation, let's say it's a two-dimensional system where we rotate about the z-axis so that z is unchanged. All right. So let's say we rotate a coordinate system. So this will be x and y. We have a new coordinate system. Prime and y prime that's rotated by some angle epsilon. Alright, so hopefully you remember from undergrad that you can write this transformation as x prime is equal to x cos epsilon minus y sine epsilon, and y prime is equal to x sine epsilon plus y cos epsilon. If you don't remember this, think of a rotation matrix. Okay, so now we want to find the f and g, so therefore the infinitesimal version of the transformation. Okay. So for an infinitesimal rotation, we go from epsilon to delta epsilon, and delta epsilon is very small. So cos of something very small is roughly equal to 1, and sine of something very small is roughly equal to something very small. So let me plug that in to the transformation equation. So we have x prime equals cos of delta epsilon, which is 1, times x, minus y times sine of delta epsilon, which is like delta epsilon. So it's minus y delta epsilon. Similarly, y primed is x times sine delta epsilon. So that's x delta epsilon plus y cos of epsilon, and cos of epsilon is roughly equal to 1. So you can write the infinitesimal rotation this way. And so that tells us that fx is equal to minus y, and fy is equal to x. Of course, in a rotation, z prime is equal to z, and t prime is equal to t. So we find that fz equals 0, and g equals 0 as well. Okay. So that's how you find these f and g coefficients for infinitesimal transformations. So let's see what a good stopping point is. All right, so we'll get started in the next section, but we're not going to have time to finish it. So this is probably one of the most influential, maybe, theorems in physics. It's called Noether's theorem. And so we'll spend a lot of mathematics time proving this. Okay? So what does the theorem say? The theorem says that any continuous transformation that leaves the action unchanged is associated with a conserved quantity. So remember, the action is the integral of the Lagrangian, right? So let's say that we have S, the action, which is equal to the integral from some time ta to some time tb of the integral of the Lagrangian, which I'll write as qi dot, and t, because I don't want to write q1 dot dot all the way to qn, right? So when I write something as a function of qi, it presumably depends on all of the q's and all the qi dots. Okay? So to say that the action is unchanged under a transformation of variables means that this integral is equal to the integral over some different range in time, so some transformed time, ta prime to tb prime, of the Lagrangian of the transformed coordinates qi primed, qi dot primed, and t dt. So it means that this equality is satisfied to say that a continuous transformation leaves the action unchanged. And you note maybe, oops, I forgot the dt in the first integral. You note that I didn't put a t prime in the integrand of the second integral. That's because t gets integrated over, right? And so it's just a dummy integration variable. But the limits are changed from t a to ta prime and tb to tb prime. Okay. So the theorem tells us that if delta S equals 0, then there is a conserved quantity. Yeah, question? That's right. So the QI primed are transformations that, like the ones we just did in the examples. So continuous transformations. And continuous transformations means that they can be written as an infinitesimal transformation. So, you can say like the rotated QIs, and then you can take the time derivative of those transformations, and you get the QI dots primed. Does that answer your question? Okay. So what we want to do here is we want to consider the infinitesimal case. So what we really want is where S is equal to integral of TA to TB of L of the QI dot, and T dt. We want it to be equal to the action after an infinitesimal translation. So that means that TA goes to TA plus delta TA, TB goes to TB plus delta TB. That's the change in the limits of the integral. And then the Lagrangian is the Lagrangian of QI plus delta QI primed QI dot plus delta QI dot prime and T. So a couple things to note here. Oops. I wrote the QI primed as QI plus delta QI primed instead of QI plus delta QI as I had in the past. All right. And so I wrote that QI primed is equal to QI plus delta QI primed, not QI plus delta QI. So what do we mean by delta QI primed? So we're varying potentially two different things. We're varying time and we're varying the coordinates. Right, so QI prime can be different than QI not only because we've shifted the rotation axes, but also because that transformation might include time in it. So we have to be a little bit careful. So this is pretty much the trickiest part of the derivation, is to understand this. So that means, in principle, we want to write QI primed as QI plus delta QI plus QI dot delta T. And then there'll be other terms in there that have products of delta QIs and T's. So this is a first order Taylor series for QI primed, where the QI prime can depend on the QIs and T. And so if you vary the Q's and T, then when you apply the chain rule in the Taylor series, there's going to be terms that have delta QIs and terms that have delta T's and terms that have products of the two. But those terms are really small. And so that means that this delta QI primed is actually equal to delta QI plus QI dot delta T. And that's a good stopping point. Is it? Let me just box this. I guess I have to make one more comment. How do I justify dropping the cross terms that have delta Q's times delta T's in them? Because they're second order small. So we do that all the time, right? We've been doing this. Ultimately, it comes back to the fact that we're trying to find stationary values of things. Okay. So let's say you want to find a stationary value of a function. So that means you want to find a minimum, a maximum, or an inflection point. So you only need to consider the first order derivative, right, to find if it's stationary. If you want to know if it's a minimum, a maximum, or inflection point, then you need to know the second order derivative, and then you would have to carry those terms. But Hamilton's principle, which apparently explains all of classical mechanics, only requires that the action be stationary, and it does not require us to know if it's a minimum or maximum. So that's, fundamentally the reason why we don't care about the second order terms. Okay? So I'm afraid I have to stop this lecture here today for personal reasons. But I'll be back on Monday, and then we'll continue on. If you're trying to read ahead in the notes, you can skip chapter 6, which is applications of the Lagrangian, because the next material we'll cover is the Hamiltonian. And we'll come back to the applications if we have time at the end of the course. Okay? All right. Thanks, everyone. We'll talk to you all on Monday.